Good morning, all. Today we are going to start the second day of the FDP program. Today we have the two distinguished guests, Dr. Prakash from University of Madras and another one, Dr. P. Chinnamuthu from NIT Nagaland. It is my pleasure to introduce Dr. Prakash. Dr. D. Prakash, Assistant Professor, National Center for Nanoscience and Nanotechnology, University of Madras, Kinti campus. Earlier, he worked in Department of Medical Biotechnology, Chettinad Hospital and Research Center. Before that, he worked in IIT Madras as a postdoctoral fellow in Department of Metallurgical and Material Sciences. He did a PhD in Material Science at Madras University under the guidance of Dr. S. Ramasamy, former coordinator of the National Center for Nanoscience and Nanotechnology, University of Madras. He did his MPhil thesis in the field of preparation and characterization of polymer-based thin films material at Bharati Yar University. He has received so many research grants from various funding agencies from like DST, UGC Startup, SERB and DRDO NRB scheme, RUSA and SERB scheme. Totally he has received 1 crore 10 lakhs for different projects. He has published 50 plus international publication. He delivered different lectures at different places in the national symposia and different guest lectures. His citation is 1272. As of now, he has a H index 15 and I10 is index is 23. We are delighted to have your lecture, sir. Thank you, sir.
Good morning, everyone. Is it audible, sir? Can I proceed, sir?
Yes, sir. Please, sir.
Okay. So, first of all, thank the organizing committee members for inviting me to deliver a lecture in this online faculty development program. So, my presentation topic is nano-enabled X-ray sensors and shields. During my presentation, at any point of time, participants may stop and interact with me without any hesitation. So, I am from National Center for Nanoscience and Nanotechnology, University of Madras, Dindi campus. It's in Chennai. So X-rays are widely used in different applications. Initially, it was around 130 years ago. German physicist Röntgen developed this technique. Okay, X-rays. He produced it with the help of Coolidge tube, and in the year 1895. So left side, what you saw is X-ray image taken by Professor Röntgen. Later, for this invention, he also got a Nobel Prize in the year 1901. 1901. Okay. So X-rays are widely used in different applications since then. X-rays are classified into two categories. One is soft X-ray and hard X-ray based on energy. In the case of soft X-ray, it is useful for X-ray crystallography, X-ray diffraction, electron density mapping, structure identification, phase purity analysis, those things. Then in the case of hard X-rays, it is used for diagnostic purpose, mammogram, CT scan, otherwise airport screening like that. So in diagnostic X-rays, there are more than 15 diagnostic X-rays are there. It's all X-ray based. Dental, intraoral, mammogram for the soft tissue female, and CT scans, body CT, head CT like that. In all these 15 techniques, X-rays are utilized for diagnostic purpose. In all the case, depending upon the organ interest, region interest, you have to expose certain dose. For example, in the case of intraoral, it is around 0.08 millisievert, whereas in the case of body CT, it is around 10.6. The difference is mainly because of density of the organ. Then, so what you have to do, particularly if you are concentrating intraoral X-ray, this is lower jaw image and lower jaw digital image, and the blue color one, what I show here is X-ray sensor. With the help of this X-ray sensor, you may capture X-ray image of your tooth. Okay, there are two options. One is direct conversion, another one is indirect conversion. In our lab, we work with both the logic, direct as well as indirect. Direct means under the illumination, your material attenuates and electron hole pair generates. You have to capture the electron hole pair. Whereas in the case of indirect conversion, X-ray falls on a scintillator that scintillates visible region or UV region, near air region, right? You have to capture that one with the help of photodiodes. So these are the two logics, direct conversion and indirect conversion modes are available, particularly if you are interested in developing this sensor. In our lab, with the help of SARP funding, two different projects, we started concentrating such an X-ray sensors, and those results only I am going to discuss today. Anyway, X-ray interacting with material or specimen, you may explain interaction with the help of different physics concepts, coherent scattering, quantum scattering, photoelectric interaction, path production, like that. I'm not going to those things. Any simple physics book able to explain all those things. Point here is, here in this slide, you saw a gray region, right? It is your specimen. Just assume it is your specimen. From the left side, you are exposing X-ray. So X-ray photons are getting penetrated or attenuated, otherwise getting scattered. It all depends upon the material nature. I repeat, X-ray photon from the left side falls on the top of your specimen. It may be penetrated or attenuated, otherwise getting scattered. Okay, it all depends upon unique nature of the material, but the primary one is attenuation. Here I equal to I naught e power minus mu rho x. This particular formula helps you to understand this concept. I naught is initial intensity and I is after penetrated. Mu is your attenuation coefficient, rho is the density and thickness of the specimen. All of you are aware that lead is capable of blocking X-rays, right? So there are alternative material you may explore instead of lead if that material have certain specific qualities. So mu is a key parameter, mu equivalent to rho z power 4 by a e power 3. Mu is the attenuation coefficient, rho is the density of the material, z is the atomic number, a is atomic mass, e is the incident energy of the X-ray. So with the help of all these, you may predict alternative material and utilize it for X-ray detection or X-ray shielding purpose. So far, if you have any questions, you may ask now. Otherwise, I am going to proceed with the next slides. So here I have an online resource. It's called NIST XCOM. In this NIST XCOM, I'm able to put any such material. For that, I'm able to get photon energy dependent attenuation coefficient plot. Okay, with help of NIST XCOM online resource, I'm able to generate this plot. X-axis is photon energy in kiloelectron volt, and y-axis is total attenuation. So in this graph, if energy is more, I'm unable to get attenuated. If energy is less, I'm able to attenuate. Okay, you also be able to see the attenuation plot for three different material: bismuth iodide, mercury iodide, lead iodide, almost all showing superior attenuating nature in the lower energy. I am interested in 70 kiloelectron volt because we have a facility that operable in 70 kiloelectron volt. Okay, any doubts, Pa? Next slide. So here what you saw is a periodic table. In this periodic table, just to concentrate lanthanides, lanthanum to the lutetium, it is around 57 to 71. If I am going to blend this with oxygen in the sixth column, otherwise sulfur, selenium, tellurium, I'm able to get a binary compound, right? Lanthanum oxide, lanthanum sulfide, selenide, telluride. Okay, just by looking the number Z, lanthanum is 57, oxygen is 8, so the net atomic number is less than 60. If I am going to blend lanthanum with tellurium, the net atomic number is more than 100. So just by looking this net atomic number, you will be able to get a conclusion. Instead of lanthanum oxide, lanthanum telluride is more attenuating because mu is directly proportional to the Z, right? Okay. So what I did is I I did a plot for lanthanum oxide, sulfide, and selenide telluride. Then from that plot at 70 kV attenuation alone, I just noted down here and plotted like this. It's called the heat map or color grid for all the system from lanthanum to the lutetium. I did a plotting and got this color grid. Here you will be able to see different colors, right? It's all you have to compare with this scale bar present in the adjacent from green to the red. So red is more attenuating as compared with the other color here. 4 and this one is 9. So just by looking the plot, instead of lanthanum telluride and lanthanum oxide, if you are comparing yourself, unable to see much difference. Whereas in the case of lutetium, instead of lanthanum telluride, lanthanum oxide is more attenuating. So here a point is unclear. Why it is like that? Because Z is more for the telluride as compared with oxide. So what we did is we also did the density heat map for all those material. In this plot, you will be able to easily saw around 15 elements in the y-axis and x-axis 4. So totally 60 plots are there. From the 60 plot, I took this particular data and got this heat map. Like attenuation here also you have to compare with the scale bar present in the adjacent. So as compared with any other material in this slide, lutetium oxide is more attenuating. So like this, what we do theoretical prediction and select a particular material, then apply it in our research. So it's because of the theoretical prediction, we are able to get successful result in our research. Similar manner, what I did is I took a couple of other material, particularly silver based compound, silver bismuth sulfide or cesium silver bismuth sulfide, something like that. I mean, A site is I am varying, B site I am not varying, C site I am varying, oxygen, sulfur, tellurium, selenium, like that. From this analysis, again I got silver bismuth sulfide is good attenuating material. Okay. So I prepared this material with the help of a chemical process, then process it, apply it for my purpose. So here what I am showing here is an SCRB funded equipment. We have a Keightley source meter, 2450 model, and a dedicated intraoral X-ray machine. In this X-ray machine, I am able to vary duration of the exposure. So it was calibrated one. If I am varying the duration, I am able to vary the dose exposed. Dose in the order of milligray or millisievert, right? So apart from that, we have an RBG sensor also, imaging sensor. With help of that, I am able to capture X-ray image of my specimen. I hope now you all understood the basic concept behind the X-ray attenuation. So now from this slide, I am going to apply my material for device development, direct conversion logic. Later, I am going to explain indirect conversion also. In this direct conversion, primary aim is to sense low dose X-rays. Okay. So here we employed a wet chemical process. Silver nitrate, bismuth nitrate, and thioestimate was used. It's all mixed together. Then washed my product with the help of distilled water to get a silver bismuth sulfide nanocrystals. It was calcined in a different temperature to get grain growth as well as variations in the morphology. So in this slide, what you saw is X-ray Ripple refinement, XRD pattern Ripple refinement. Material was, as prepared material was processed at 150 degrees Celsius for different duration. Okay. So with the help of that, we got XRD pattern, and the red one here are data obtained from the instrument. Black lines are fit, and you have green color hyphen here. It's all Bragg's positions. So how perfectly our sample matches with the standard was identified with the help of this fit. The difference difference between data and the JCPDS was mentioned here in blue color. So like this, we do ripple refinement to confirm our phase purity, our sample phase purity. So for that, we mainly use here goodness of fit. Here chi-square is, I mean, all the case, it's all less than 1.5. It's a good fit. So like this, we confirm. After the confirmation, we also do grain size distribution from the data from the XRD pattern analysis. A simple procedure is there. With the help of that, we also get the grain size distribution. 1/4, 3/5, like beta value you have to extract from the 100% peak and get a plot like this, grain size distribution plot from the X-ray diffraction. Next, what we do is, I already told, right? Here, this is the gray color one is your sample. You are exposing X-ray from the right side. If it is getting attenuated, then we are able to measure its conductivity. If it is not attenuating, it is penetrating, then we are going to get lesser current, conductivity lesser. If my material is more attenuating, more current I am able to get. The simple logic we are going to do here. Once again, any clarification is needed so far?
Sir, I have one doubt, sir.
Little louder, pa.
Myself, Dr. Ajit, sir.
Okay.
I have one doubt, sir. Sir, you told about break positions.
Yeah.
Positions. So, on what basis, which break positions you are considering? Because many break positions are coming there. In
Sir,
which range you are considering the break positions?
Sir, your voice is not clear. What I understood is your question related to the grain size distribution. Is it correct?
Yeah, break positions.
Yeah.
Break positions, which range you are considering in the break position? Because many break positions are coming. In which range you are selecting?
For the grain size distribution, you have to consider only 100% peak. From the 100% peak, at different places, you have to measure distribution, beta value. After subtracting instrumental Browning, then you have to account it for a calculation. We have a formula called, a method called 1/5, 3/4 method. I mean, beta value extracted from 1/5, 3/5. With that, we are able to get the distribution.
Okay, sir.
If you are still unable to understand that one, later you may collect my number. You call through my mobile. We may discuss it further. Okay. There are literatures available, but many of us not using X-ray for this purpose. We use most of us use only TM for this purpose. The XRD also one can able to do.
Okay, sir. Thank you.
Okay, so then we do X-ray, after XRD measurements, we do also SEM to confirm the morphology, composition, everything. Then distribution, from the image analysis of this low magnified distribution, we are able to get grain size distribution. So far, one of the participants discussed how one can able to get distribution from the XRD. From the XRD also you may get distribution. TM also able to get distribution. From UV visible spectrophotometer also data analysis also one can able to get distribution. So among these three, XRD is more accurate as compared with TM and UV, because here you have to sonicate, and from the sonicate a drop of the dispersion was used to visualize the morphology. From the morphology image you may get the distribution, right? If I magnified, then D-space measurement one can able to do. With help of that HKL orientation one can able to assign. This is electron diffraction. This is an electron diffraction pattern. Using image A, we convert 2D into 3-dimensional image like this. Then because it helps us to differentiate the rings and properly analyze the SAD pattern. After analyzing, we also assign its HKL values to values. It's all familiar to you, right? So here the main thing is from the PCB board. We took a commercial PCB board. It's a plastic coated with the copper. So from the copper, using Bettage process, we are able to get a patterned copper like this. On the top of this patterned copper, we coat gold or silver, tin, then we able to get this. So in this particular image, copper coated with tin. On the top of this, we coat a thick film by glass rod sliding like this. Then these two pads are connected with a source meter. Under the illumination of X-ray, we are going to measure X-ray instigated photocurrent. So like this, the left side black region was your specimen, digital image. The middle one, second one is X-ray image. X-ray image. You will be able to see a electrode as well as material coated on the top of it, right? So for this specimen, we are going to measure photocurrent, X-ray under different duration I'm going to expose. So for that, I'm getting a positive square wave. The yellow color marked region alone, I'm going to expose X-ray. Other regions are not exposed. So I'm able to get a positive square wave. So for all the crystallite size, what I found, a particular size exhibits more photocurrent. So my prediction is we propose a model for this. It's called multiple scattering.
Sir, Prakash sir.
Yes, sir.
Sir, your voice is not audible.
Sir, due to some network issues, the speaker will join soon, sir. Sorry for
Yes, sir.
the
Yes.
confusion.
Okay, okay, sir.
Participants, sorry for the inconvenience. I hope all of you now see my presentation. Is it
Yes, sir.
visible,
It is
Pa?
visible.
Yes, sir.
Thanks. So in this case, this is my electrode. On the top of the electrode only, my material was placed, and the pads are interfaced with the source meter. On the bottom, you have an X-ray sensor, RBG sensor, X-ray image of our specimen. We are exposing X-ray and measuring photocurrent like this. Like this. From the dark current and the X-ray current, we are able to calculate sensitivity For different doses, we are just plotting ETH like this. It's all linear. The sensitivity observed here is linear. Is it all?
Sorry if I have taken misconnection. You can start.
Yeah, no issue, no issue. One second. So with the help of the sensitivity plot, you will be able to understand dose dependent sensitivity was linear, and grain size effect, what you saw is working well. For a particular size, we are getting more sensitivity. Just to concentrate here, 7.97 milligray dose, we got around 20 microcoulomb per milligray. Such a high sensitivity we observed for this particular material. Okay, I told you earlier itself, we are varying the duration of the exposure. Our machine was calibrated with the help of the calibration. I am climbing here 3.2 second. If I am exposing, it is exposing 7.97 milligray. Like that, duration was varied, dose was varied. So in the next slide, what you saw is we propose a mechanism like this. I already explained to you, right? If the sample consists of bigger grain size, the attenuated going to give you electron output generation, but scattered was unutilized, so you are going to get lesser photocurrent. If you have sufficient grain boundary contributions, so scattered from the grain getting attenuated by the grain boundary, so I'm able to get a little more current as compared with the bigger grain size. The lower grain size don't have grains, right? So such a case also I'm going to get lesser grain size. So here in the right hand side, what you saw is grain size versus sensitivity plot. For the lower grain size, I am getting some value. For the higher grain size, I am getting some value. But the size was size consists of both the contributions, grain and grain boundary contributions. I'm able to get here little superior sensitivity. So here for the 54, I am getting around 20 milligray, right? Microcoulomb per milligray, right? So we wrote a paper and submitted into sensor and activator. It got accepted in 2023. The next concept what we did is we wish to segregate in the grain boundaries with the cerium oxide. So in my earlier theoretical prediction also confirms cerium oxide is little attenuating, I mean superior attenuating. So we took that one small amount of cerium oxide nanocrystal and microcrystal separately segregated in the grain boundaries of a 54 nanometer grain based silver bismuth sulfide. So it was schematically shown here. The yellow one here is cerium oxide, and red one here is micro cerium oxide. Okay, the black ones are silver bismuth sulfide 54 nanometer grain. Okay, so with this logic, I got two material. One is nanocrystalline cerium oxide segregated silver bismuth sulfide nanocrystal. Another one is micro cerium oxide segregated silver bismuth sulfide cerium oxide. So for both the sample, we coat on the top of our patent electrode, then measured its X-ray instigated photocurrent. Preliminarily, we also characterize XRD and TM, SAD pattern, distribution, thickness here with the help of scanning electron microscope, cross-sectioned specimen. So here for the micron ceria segregated grain boundary sample showing some current, whereas whereas in the case of nano based, it's showing little superior current. Okay, with the help of the current observed, area, dose exposed, we are able to calculate as like previous sensitivity. Here what you saw is the sensitivity is now getting enhanced from 20 to now 28. Such a small enhancement also play a crucial role in imaging an object. So this one again submitted to the sensor and activator same journal, and it got accepted in the same year. So far what you saw is direct conversion logic, material getting exposed to X-ray instigated photocurrent was measured, Then sensitivity was calculated. We propose a mechanism and getting a paper published, right? The second logic is indirect conversion logic. Here, X-ray falls on the specimen, but it is not creating electron pair. Instead, it is emitting light. Okay, it's called scattering. It's called scintillation. So we employ such a trick and develop a low dose X-ray sensor. We took here two different samples. One is cesium lead bromide, another one is cesium copper iodide. Both the samples put it on the top of photodiode, commercial photodiodes. Okay, here what you saw is commercial photodiodes. On the top we coat our material. The first one is cesium copper iodide based. The lower one is cesium lead bromide based. Both was coated on the top of photodiode. Its X-ray alternating image was captured with the help of RBG sensor. So in this D image, you will be able to see a photodiode in a bright color and gray color. On the top, you will be able to see a small thick gray, right? It is your material, cesium copper iodide. Similar manner in the case of cesium lead bromide also, we did a coating like that. And for this, before coating, after coating, then under light, under dark, we do IV measurements using the same source meter, IV. Okay. So now under illumination of X-ray, we have to do IV measurements instead of IV, IT measurements, current and time measurements. Before going to that, we also measured its thickness. Without cutting any sample, we just give the photodiode to the SEM technician and he measures the thickness of the coating. Each one have specific thickness. We account the thickness. So this is our modified setup now. This is our X-ray equipment, photodiode coated with our material, interfaced with source meter. Source meter is connected with our system. So automation, we are automated one. So we are able to calculate, we are able to measure X-ray instigated photocurrent. Then RBG sensor interfaced with again system. I'm able to capture X-ray image. As compared with the direct conversion, here I am able to get a negative photocurrent. I hope all of you understood why I am getting negative photocurrent. For a photodiode, if I am exposing light, I am able to get negative current. Okay. Similar logic here, my material under the illumination of X-ray, if it scintillates, my sample is in a dark. Scintillates, because of the visible light emission, I am able to get a square wave here. Okay, I am not exposing any other photon. The exposed one is X-ray photon alone. So this particular photodiode was kept in a plastic box. Okay, so without any external photon getting exposed, visible energy photon getting exposed, only X-ray photon is getting exposed because our X-rays are able to penetrate plastic container. Okay, black box we have. So that's why I'm getting here a negative square wave as compared to the previous case. Again, like previous case, dark current, X-ray instigated photocurrent, dose exposed, thickness of the specimen, area of the specimen helps us to calculate sensitivity. Dose dependent sensitivity here also it is linear. So this is another new logic, right? So we proposed this work to the SARB and got funding also. And that work was published here in material semiconductor processing. Here the dose was exposed for different durations, right? So I'm able to get a linear trend and climb. I prepared a low dose indirect conversion X-ray sensors. Here the dose measured in the order of milligray. The next slide, what you saw is we also do X-ray shields, because if the dose was exposed to the lower jaw, after examining the specimen, X-ray photons may also falls on the thyroid gland. So thyroid gland may get damaged because of the X-ray photons. Okay, there are literatures are available. If it is upper jaw, brain may get exposed to the X-ray. Okay, repeated screening or long-term exposure may damage thyroid gland, otherwise brain. Okay, if it is getting damaged, body going to repair it, but if it is unable to repair it, then it may trigger radiation-induced damage, right? It may trigger cancer. Okay, thyroid cancer, otherwise brain cancer, something like that. It all happens because of the X-ray exposure. So this is our setup, X-ray photodiode stage. We coat our sensor with coated one photodiode coated with our sensing material. That one was kept here. This is our black box. We keep our specimen on the top of this bridge, then close it the lid. In order to understand the logic, I just kept my specimen on the top of the container, and this is our X-ray source. So these are all our specimens. Just we are now exposing X-ray, and our sensor going to capture X-ray instigated photocurrent. Okay, but if my specimen is not allowing my material to my X-ray photon to penetrate, then I'm unable to get. So primary aim is we wish to block X-ray. So we used to develop X-ray sensors. Here I took again a material, barium ferrite. It's an odd magnetic material, X-ray refinement, odd magnetic material, barium ferrite. So hysteresis measurement to climb it is odd magnetic material. So this is our specimen now. We blended with the resin and got these bricks. And for these bricks, we are going to measure X-ray instigated photocurrent. These materials are just creating, I mean, it was kept on the track of X-ray photon. X-ray photon is incident on my photodiode, right? We are just keeping this material as an interface, so it may block or penetrate. So this is for the photodiode, and it is getting suppressed, right? Because of the barrier we create with the help of this specimen. So if I am able to achieve 100% loss in X-ray instigated photocurrent, it means I am blocking all the X-ray photons. X-ray photons are not false on my sensor, right? So X-ray shielding efficiency was calculated for different composition. We found that almost 90% of efficiency for the particular composition. Okay, I hope this concept also clear to all of you. Apart from doing research, we also popularize nanoscience to the young minds. We conduct workshop on nano at different places. This is in a college in Thuthukudi. It's called St. Mary's College. There we went, our team members helps them to learn nanoscience. We do a couple of material preparation, different methods, different applications. We train, we transfer our knowledge to the participants. If you have any questions, I'm ready to answer it. Before that, this is my student, Dr. Karthika. She only carried out this X-ray instigated work and published a couple of papers, got awarded doctorate. Now she is in Silver Ray, it is in England, serving as a research scientist. That particular industry, Silver Ray, develops X-ray sensors. So, since she works with X-ray sensors in her doctoral research, she easily got a position there. It is an industry. She got placed in industry, presently getting around 4 lakhs per month salary. With this note, I thank all of you for your attention. If you have any questions, doubts, I'm ready to clarify it. Thank you all.
Sir, I'm having one doubt, sir. Hello,
Sir,
sir.
little louder. Yeah.
Yes, sir, I'm having one doubt. So you have used the patterned electrode for coating of the material. My question is, sir, that what kind of patterned electrode you have used? It is made up of which material, which substrate?
What kind of material you used? Is it correct?
For the patterned electrode.
Patterned electrode. Okay. So for the patterned electrode, what we have to do? You have to anyway go through my literature. You will be able to create patterned electrode. What you have to do? You have to purchase commercial PCB boards. Okay. It's all plastic boards. On the top of plastic boards, you have copper coated, commercially available, 90 rupees. Plate available. We collect that one, and the top we create pattern. For that, what you have to do? You may create a pattern in your computer. Take a printout using photo sheet. Then that printout you have to keep it on the top of a cleaned copper surface. Then perform art press. So this pattern was transferred on the top of the copper. Then use iron chloride for etching it. So unwanted regions are getting etched you also be able to get a clear copper pattern. On the top, you may perform electrode deposition or electrolysis deposition. You may coat any metal on the top of copper and create a pattern. Copper patterned electrode. It's called interdigitated electrode.
Sir,
You refer my paper.
sir, which pattern making, sir? For what purpose pattern is needed?
Okay, 1 second.
Yeah.
My slides are visible to you, right?
Yeah, correct.
So here, this is commercial copper PCB board. A small piece was cutted. Then we created weightage derived pattern. For this,
Okay.
you refer my paper. On the top, we create coat tin, gold, silver like this. So this is our patterned electrode.
Okay.
Both the fingers are not touching each other, right? From the pad, I am able to take the heat. You may create such a patterned electrode using thermal evaporation also, but in order to, we don't have such a facility, so we created by using this. Then on the top, we coat thick film and do the measurement. I hope you now understood.
So there is one working and one counter electrode, correct?
This is photoconductivity logic, so
Yeah.
there is no need of both the electrode. Only one electrode is needed.
Okay.
Working electrode is.
Okay. These electrodes are regenerative, or every time we have to use new electrode?
Each and every time we prepare new electrodes for
So
one particular system.
So this cannot be regenerated.
Because our coatings are well adhered on the top of my electrode. Okay, that's why after cutting it, we measure its thickness using cross section the same. So no need of reusing it. It's all very cheap only, right? 90 rupees, yeah, board. From the 90 rupees board, I'm able to get around 20 electrodes like this.
Okay. Okay, sir. Okay. Thank you very much.
Yeah, you may refer my paper. If you are able to follow, then well and good. Otherwise, reach me through my email. I'm able to share those informations to you.
Okay, sir. Okay. Thank you very much.
Thank you. Any other doubts, participants?
Sir, there is one question in the chat box, sir.
Once again, sir.
How to download JCPDS card in or any software?
You have to use a software called PCPDF Win. It is a paid version, PCPDF Win. Okay, PCPDS Win. This not Win. Okay, this one is not free software. It is commercial one. But instead of this, you may collect zip file. Okay, from the crystallographic deposits, you may collect zip file. Okay, using that zip file, you perform ritual refinement. So without JCPDS, you may collect zip file and use it for your purpose. JCPDS software, what I told is PCPDF Win. It's a paid software. You may collect from your friends. Otherwise, send an email to us. We will share the JCPDS card to you. It is not free one, but zip files are free. You may download and run your ritual refinement, index your sample. I am here sharing my mobile number to all, email ID also. If any queries or need any query or any collaboration or any support is needed, you may approach me through this WhatsApp number, otherwise email. We also do workshops on nano, otherwise ritual refinement, TM image analysis like that. You may go through that. Otherwise, you watch our YouTube channel. Our lab research scholars also running a channel called Nano Optoelectronics Lab. I repeat, Nano Optoelectronics Lab. It's a YouTube channel. In that one, we also explained ritual refinement concepts, how to install your software, how to learn ritual refinement, TM image analysis, low MAC, high MAC, SAD pattern analysis. So go through that. Still, if you are unable to understand, you may visit our lab. Otherwise, you may invite us for a workshop. we will help you to learn. Any other questions? Any free softwares are available. There are softwares, but it is not for JCPS. You may index your XRD pattern, otherwise SAD pattern, TM image analysis, right? For TM SAD, you may use ImageJ software. For XRD, you may use XRDA 3.1 version. Otherwise, Expertise Score, Basic, Silen, like couple of softwares are available. If you have JCPS card, then for the comparison, you may use these software. Otherwise, you have to use Pulfrof only. Pulfrof, using zip file, you will be able to run and compare your pattern is matching with the standard or not using the Ripple refinement procedure. Any other question? Participants, if you have any other question, I'm ready to answer.
Sir, there is no more questions, sir. Thank you, sir. Thanks for your enlightened lectures. So I have
Thank
already
you.
given your address in the chat box, sir.
Yeah, I saw it. The
Thank you, sir.
second email ID, you know, all of you, the second email ID sometimes not works. University email ID not works. So use our Gmail account, Gmail email ID for the communication. I hope all of you understood today's my presentation. If you have any queries, without any hesitation, you may approach through this email as well as WhatsApp. Thank you all for your attention. Thank you.
Thank you, sir.
Thanks. Can I leave, sir?
Yes, sir. Chinnamuthu, sir, shall we start, sir? Sir, good morning, sir.
Yes. Yes, sir, we can start, sir.
Yes. So it is my pleasure to introduce the second speaker, Dr. P. Chinnamuthu. Dr. Chinnamuthu was born Tamil Nadu, India in 1984. He has received the BE degree from the Department of Electronics and Communication Engineering, Anna University, in the year of 2008, and MTech from Pondicherry University in 2010, and PhD from National Institute of Technology, Agartala, in 2013. He worked as a postdoctoral fellow from April 23 to March 25 in Advanced Device Material Group, Nano Electronics Materials Unit, International Center for Materials or Nano Architecture, National Institute of Material Science, Ibaraki, Japan. He is currently working as an associate professor in NIT Nagaland from March 22 to at present. His research interest includes the fabrication of 1D metal, metal oxide, semiconductor nanostructures, combinational synthesis of K materials, thin film growth, nano electronics and optoelectronic device fabrication, cost management in the power sectors, IoT-based healthcare monitoring for healthcare applications, and smart agriculture with IoT agriculture applications. Also trying to minimize nature for self-cleaning applications. He has more than 10 years of research experience, and he has published more than 50 publications in different reputed international journals and conferences, book chapters. He has delivered the more invited talks in the different conferences and workshops in the different field. We are happy to hear you, sir. So, sir, please, sir.
Yeah, thank you so much for the nice introduction and for welcoming and inviting me to share some knowledge which I have in my the career which I have gone through. And today I'll be talking about my before that one, my voice is clear, and then I just wanted to know my presentation is visible.
Yes, sir, your voice is clear, sir.
Whether could you be able to see my presentation?
Slide is visible. Just
Okay.
you can change one or two, sir, whether it is moving. It's moving, sir.
Okay, thank you so much. Okay, thank you so much once again, and for the giving opportunity to share my view and my experience, what I have gone through for this the year throughout my research journey. Then I'll be sharing, and then I always try to make some curiosity among the audience. I try my level best to create a curiosity and to do some work on that particular one. Before I go into that, my research topic, and then this is the picture which I kept it as a wall, like the this one. And this is our institute, which is located in the northeastern part of India, and in Nagaland, the state of Nagaland, and we are very well connected with the railway station as well as the air. Those who want to visit, and then you are always welcome. And with that one, and I'll begin what we are going to talk, or what we are going to see in the coming slides. And most of the people, those who are working in the nano, they know. But I just wanted to give some glimpse of nano, and then nanostructures, why and how to create the nanostructures and application where it can be applied. These are the things. And before going to that one, and like one Nobel laureate, he visionary person, he told the human being are going to face the challenges in coming like in 10 years. He was mentioning like the listed 10, and already we are facing so many like in the listed almost in that one, like the researchers are working to solve the challenges, to convert the challenges into opportunity with the facility, or with the which they have a knowledge on that one, and everybody is creating the challenges into the opportunity, while creating the opportunity. And when they are working on that particular opportunities, and then they are having again there is a challenges comes into the picture, like the scalability, selectivity, and the quality, and also like a compactability. Everything comes into the picture. So when we are as a the researcher, when we are looking on something, then we have to keep it in our mind how it can help the society, and also without having any hazardous, or without degrading the further the environment. So we should not hamper the environment, and then we should help the nature. The nature is helping in so many ways, and vice versa, we have to help the nature as well. So with that, I just give some the few the pollution which we encounter, then the especially like environmental pollution which we are facing, like air pollution nowadays. If you see in the winter, completely in Delhi or some the places, it is covered with completely polluted air. And also in our even in our the industry area, like the dye industry area or pharmaceutical industry area, if you see the water, most of the water, if you test the water quality, then we might able to feel the problem of that, whether it is like a drinkable, or whether it can be usable or not. And when we are using that where we are using the, whenever using that fish which is coming out of that water, then we are eating, and like we are doing each and everything in terms of soil, in terms of water, and in terms of air, and everything was pollution in everywhere we can find it. And how we can solve these are the problem with help of some nanotechnology or nanomaterials, which we think that it can solve the problem somehow, whatever it is, the challenges which we are going through. So further delaying anything, I just wanted to tell, and what is nano, I just pictorial, just try my level best to just give only that in the pictorial representation, not in the scaling level. I just put the what is a nano and why how it can help the human being, or how it can change the challenges into the opportunities. So from the size, you could see that so you can see like the sizes, it changes from the bigger into the smaller, where you can see like, the sizes which we are going to talk is about the very tiny. And if you see, it is a 5 millimeter. Human hair, it is around 60 to 120 micrometer in wide, and also in red blood cell, if you see, the 7 to 8 micrometer. So we will be talking further less than that one. So means like I wanted to tell you that we will be talking in the very tiny things which we were not able to see in the naked eyes. And uh, now further, I just wanted to say some kind of quantum confinement. The quantum confinement is when we are changing from the quantum confinement, means like a kind of restriction which we are putting in the transportation of the electrical and the carrier charge carriers. If you see that here, it is freely, the electron can freely move in all the space in all the area. And if you see in the this one, the restriction has been kept in a particular one two direction. Then only the carrier can move in only one, the axial the direction, and remaining part has been restricted to the movement. And again, another this one, quantum wells or quantum dot, and then the carrier can like move as a dot. It cannot move any other space. So when we are changing, or when we are restricting the movement of the carriers, then we can see that the density of state changes. So from that, the people motivated, when we are tuning the particular things, then we can able to change uh, the the properties of that particular material, and it can be applied in the further wherever we wanted, then they can be easily applied. So why it is nanostructures, I just wanted to tell you, is that one advantage is that when we are when we are making the nanostructures, what we can, from comparing to the bulk, the large surface to volume ratio can be increased. Like for example, if you see, you take a 1 cube of uh, square, then which having 1 meter area, then if you are the area of this cube, if you see, there's 6 meters square. Then if you are dividing that one by half, or further, if you are dividing further, the cube is same, the area of the cube is same, but it is like the which is changing from 6 to 12 to 18 meters square. So what I mean to say is that the same thing you can keep it, and then when you are reducing down the sizes, the surface to volume ratio is increasing. When we are increasing surface to volume ratio, sometimes it can increase the sensitivity strength of that particular one. It can be improved. And also another example which I wanted to tell you is that, like when we are changing the quantum size effect, especially when we are reducing the quantum, like a particle size, from the nanoparticle size, from the 100 to like less than like a 2 nanometer, or less than 10 nanometer, the light the illumination or absorption, it changes from like the color. You can see there are some color, it can be tuned, increasing or changing the particle size. So these are the things why what could be changes when we change the nanostructures, or the particle size when we are changing. And why the nanostructures are interesting is that if you see the butterfly, and then we might be wondering how, like, the butterfly has been very colorful, and then how it came, whether how the color looked like, why the color looked like it different one. So that curiosity was in the by the researcher. They have started looking, uh, taking the electron scanning electron microscope image. Then when they are taking that image, they could find that the butterfly was, the structure, that surface was having that kind of the changes, like the bone and whole, or the structure was something is different, which could see. And because of that one, the light scattering in between that one, and because of that, the refractive index changes between that bones, and as well as the air gap which is available, it changes the color of the butterfly. So that was there's something which the nature, from the nature, the scientists or researcher have found that when we are changing that refractive, when we are changing the structures, then it can change in a different things, especially in terms of the solar, or are creating some kind of difference. The nature was teaching us, or create some kind of structures where it can be used in the different application, in terms of solar cell, or in terms of the electronics applications. And without any pigment it can be done. Another thing is that, like, if you have seen that elephant which is having that the flexible kind of things, then that given the some the people to work on the flexible related things without having any problem, and without breaking anything. If you make the flexible, it can be used, and then it can be like helped in so many ways. So that was the nature was given, nature is teaching something, or providing some support to think out of the box. So that was which I wanted to tell you. Another one is that, another interesting thing, you and everywhere aware of that one, that water repellent properties, that lotus leaf which you can see, it will not absorb the water, it just repel the water. With that one, the people have started looking that the weatherproof painting, or the textile industry, they were started making some kind of the waterproof clothes, wrinkle free clothes. And also, like, nowadays in the paint, you might able to see the Asian paints, or Nippon paints, they will say the weatherproof paint, where the dust, or even the water will not hamper, and all those things. So from the nature, the people started thinking and making some kind of nanostructures, and modifying the surfaces of that one. Then with that one, that they were able to, like, see that how it can be helped. So when they were looking the images, the scanning electron images of that lotus leaf, you could see that you can find it out, the surface is little bit in a, like, in a very rough, means like it is some kind of the particles are in or hump kind of things. It is spread over the lotus leaf, that will not absorb the water. So it is always make some kind of in between the surface, and to that the air gap kind of things, it make some kind of the force which can repel the water. So from these things, the nature, through this nature, the people started working on further how it can be used, further how it can help in the human being. So these are the challenges, and challenges which we come with the help of how it can be overcome using some kind of nanomaterials. When we are making the nanomaterials are where the materials are in the nanometer size, then it can give a lot of big potential in small particles. So for example, like if you see here in Australia, there is a skin cancer is one of the biggest problem. Why? Because they are having skin burning in the because of the sun heat was very intensity very intensive, which is having the UV ray. If you see the solar spectrum of the sun, if you see in the solar spectrum, the UV intensity is high. So because of that one, many people in the Australia, they used to have a apply the sunscreen. When they are applying the sunscreen, the problem sometimes in the olden days, the people see that it's some kind of patches which they are finding. So in order to use the transparent things, they have made some kind of the titanium based or silver based nanoparticle which can be transparent and also can be absorb the UV lights and without affecting the skin. So the people started they creating the sunscreen lotion with the help of the AG particles, nanoparticle, which can be a transparent and also can be a help in or solve the problem of that the sun sun burning. And because of the sun burning, if they are able to protect that one, then they can be covered with the cancer, or they can be protected very sun heat or the or cancer, sunburn, or some the cancer which can be skin cancer can be protected from that one with help of the some kind of nanoparticles. And also even in the solar panels as well, then they had started the emission of that solar panel, creating the solar panel. And with the help of that nanoparticle or nanostructures, they have started to increase the efficiency of that the panel. And again, with help of the new structure also can be overcome the challenges that what we are facing for that one. Another one example which I wanted to tell you is that like uh, the tennis ball, if you see the tennis ball, the lifetime of the tennis ball, it may not go prolonged because of that the lifetime, the air which is pressure which is inside the tennis ball, it might be goes out. So when people are checking that one, they found that the gap between these the material which they made it, then there's some micro or the pore was there which can release the pressure very quickly. And with help of some kind of nanoparticle, and when we are the nano composite when they create, then which covered with that one, then kind of if you put the particle, tiny particle over here, then it able to try to reduce the pressure or going out, then it can increase the lifetime of the tennis ball. So and also another one, the food packaging or protective clothes. If you make some kind of composite material, then covered that one where with there are some more pore which oxygen get inside the tetra pack, and then it can create from the good food to spoiled food because of that the reaction which is get mixed with oxygen. And or the which can which can be like there's a like the lifetime of the food product can be extended if we are using some kind of using some kind of new structures or new materials which can be solved. And even the pollution also can be, if you make some kind of filter kind of things where the carbon monoxide, if it comes out of your the vehicles, can be reduced. And with this, maybe we can reduce or we can overcome the challenges with help of the nanostructures or nanomaterial when we create a different structures, or when we are making the bulk to the nano. Maybe we can overcome some challenges, of course, like can be helped with help of that one. So where these nanostructures and everything, where it can be applied in terms of the flexible, in terms of you take it as a take it from all the industry, then display industry, electronics industry, then textile, the healthcare industry, that nanostructures as well as the nanomaterials helps where it can be used. And it can be very like like applied in all the application wherever nowadays everything can be applied. Whatever we take it with help of some electronical components, if it is there, then we may able to say that these are all like used with some kind of nanostructures technology or nano devices technologies. So all the industry, in most of the industry, you can see that it can be applied. So how to make a nanostructures? Like there are two techniques. One is top down. Then what is top down is either etching or lithography. The etching is nothing but like you take some kind of big, it's like a culturing the things. You take a bulk one, and then you carve whatever you wanted or remove whatever you wanted to remove to make a whatever you like in the structures. So in the bottom up, that is another technique to make the nanostructure is bottom up. Then bottom up is that we have a mini like physical vapor deposition, chemical vapor deposition, plasma enhanced chemical vapor deposition, molecular beam epitaxy. Then like there is a many, and out of that one, then I'll be talking mostly about the physical vapor deposition, which I have worked for almost 10 years. More than 10 years I was working in the physical vapor deposition technique. Then how I have made structures. Then before going to making the structures, there are some technique which I wanted to tell you is that oblique angle deposition. The oblique angle is nothing but like if you make the inclination, the deposition, then you see like this is the your deposition source or source material, then this is the substrate holder. Then if you are making the particular inclination between the source as well as the your substrate holder, then the wafer like you can see it is like a wafer is coming in the inclined one, then it is deposited, and then you can able to see the one particular the direction of the growth. You can see it is in the particular orientation. And the glancing angle deposition is the advanced version of the oblique angle deposition. Here like if you see sometimes like inclined way the deposition, if it is this is the source material, then this is your substrate holder. Then if you are having the inclined deposition, what might happen is that it might have the randomly orientation might comes into the picture. So in order to make like vertically aligned in a structures like this one, then like we have to make some kind of physics, simple physics which we have to play. then how it is like we have if you are the wafer comes into the substrate, like it is we can be separated in two the components. One is a parallel and then perpendicular components. When we are the parallel components only gives some kind of the different orientation, the making the orientation of the structure. In order to make a vertically aligned structures, we need to cancel the parallel component which is coming out of from the source material. The wafer comes out of the source material. So for that one, the simple physics is that, like if you do one azimuthal rotation with the inclined one, then we can able to, after one successful rotation, that with the opposite this one, when after the one successful azimuthal rotation, that the parallel components, the force of the parallel components can be cancelled, and only you will be having the perpendicular components which comes out of that one to the substrate. So with that one, you may able to make the vertically aligned structures. For especially when you are having the vertically aligned structures, those who are working with the solar cell, if you are making the structures quite vertically aligned, then you can find the like the light, if it comes, then it after multiple scattering inside your nanostructures, it can be absorbed, or the most of the things can be light can be absorbed, then it can convert further to increase the efficiency of the solar cell. So these are the technique which we have done, and this is a simple the facility which we have made inside in our institute with the help of the right now the ANRF. Previously it was ACRB. They have funded one project for making nanostructures for photodetector applications. Then we procured from the high vacuum from Bangalore. Then they have provided the physical vapor deposition electron beam evaporator. This is our the vacuum chamber, and then this is a control panel, and this is an electron beam source. So this is a schematic structures. Inside that vacuum chamber, then we have made some simple glancing angle deposition with help of some motor. This is the height also can be adjusted, even the inclination angle also can be adjusted, and then rotation speed also can be adjusted. That means like a control, where when we are controlling, then we can able to make a different structures or make a different kind of things. So let me play this some video. This is the let me just a minute, give me a minute. So we have made in our laboratory the glancing angle deposition, everything. Then I'll just play this. This is the inside the chamber. This is a substrate holder, and this is over here you have a source material, and we have a motor in backside. Then it can be connected with some the cable, where it can be azimuthally can be rotated. Then inclination also can be tuned, and then this is a thickness monitor meter. Then we have a inbuilt like in a customized by our own in our institute. Then for the different types of the structures, we can able to create the whole shell, core shell kind of things, or even we can make the different structures, helical kind of structures. We can just play with the motors rotation, as well as like the height, as well as the inclination of the angle, where you can just have a very like you can make a different structures for a different application. You can play with that one, and then where it can be used. So we are also done some uh, uh, with some kind of structures, playing that changing the rotation and changing that particular the inclination angle. Then we found some interesting things. In a coming slide I'll tell you. So this is the one thing which I wanted to tell you is that then we have an inclination deposition. So we made it as the 85-degree inclination to make the nanostructures, and we checked if we reduce down to that 70 or something, then as per the tangent rule they have given that 85-degree if you are making, then you can have a nanostructures well aligned. So, but we thought whether it is working or not. Then we found that 70 degree we changed. Then when we are seeing that one, it is started creating some kind of structures, like nanostructures are trying to form, especially nano rods or nano wires or nano things. So, further, we increased from the 70-degree inclination between source to the substrate holder from 70 to 85 degree. You can see this is the top view image of the scanning electron microscope. Then you could see the nano structure has been the nano wire or nano rod kind of things, which you could see in the top view. And from this one, if you see, you could see that in the substrate the nanowires are standing in very aligned way. This is completely in the shadowing technique, which the nanowires are standing in the substrate without using some kind of catalyst or seed particle we haven't used. And then this also can be very controlled. And so that was, we found one of the interesting thing in the glancing angle deposition. This technique, no need to have some kind of the seed particle, and and also it can be completely controlled with help of some motors, and inclination can also be controlled, and also the height as well as the diameter also can be controlled. And if you find another one, then another interesting things which we explored is that the when we are changing the rotation, azimuthal rotation of that particular uh, the the nanowires has been diameter of the nanowire has been reduced from the half of that one. So we have changed the rotation from 120 rpm to 460. That means the maximum speed which we have used the rotation of that particular motor which we had. Then we were able to see the changes in the diameter has been changed from the 80 nanometer to the 40 nanometer. Then that was another big advantage or a big things which we have changed. And without doing anything, we were able to control the diameter of this one, and also that also vertically aligned, not in the random orientation. And we examined with a high resolution transmission electron microscope. When we checked, then we could find that there are it is something like that we found it's fine tree leaf kind of structure which we able to see. So we have checked with the optical absorption measurement with the help of if you see that two things we have made it a thin film, as well as the different rotation speed. And in that, when we the 120 the rotation per minute, and then 460 rotation per minute. If you are seeing, the band gap also has been tuned, and also absorption, the intensity of that absorbing intensity also changed when we are changing the structure from the thin film to the nanostructures, and also further reducing the nanowires. It is changed, and the band gap also the tuned further with help of changing this one. Maybe it can be some kind of quantum confinement effect. Then further also we have done the not only that single nanowire. We thought, okay, let me see, or let me make some kind of axial heterostructures to make the axial heterostructure for other application, whether it can be possible or not. So we have made successfully made the axial heterostructures, like when we are making, actually, like we were trying to make some kind of broadband the absorption broadband the photo detector kind of things, like when we are making, then we found that like so the absorption intensity of that particular the material, the structures which we made it, if you see that the intensity has increased when we are making the axial heterostructures. And and also we were able to see some kind of the enhancement in the photoluminescence effect as well when we are making the different structures, that we can able to find out make some kind of different things. And further we have checked the photo current measurement and photo the uh, uh, like a sensitivity or the light on off condition which we checked. And particularly if you see that single nanowires means one material wire if you are having, we were able to see that when we are making the axial nanostructures for with the help of the titanium and then indium, then it is having that the particularly in the UV region, the responsivity is very high. Of course, like the material which we have used, the titanium as well as indium oxide, it is having that the both, it is having like in the UV material, and also like some portion of that visible region also has been seen, the responsivity also given in the visible region as well. So we could find, after making the nanostructures, we were able to tune further, even not only in the UV as well as in terms of in the visible region also can be taken or it can be seen. So, and also like the light on off the responsivity when we are checking the rise time and fall time when we are checking, and the axial heterostructure was shown that very quicker rise time and fall time, then which can be the another the evidence with the help of the nanostructures, where you can means like a axial heterostructure, you can able to do the changes are can be applied in the different applications in terms of the optoelectronics or the photo detector applications, which can easily sense quickly it can down. So another things we have studied further in terms of the memory application, which we studied further, then the axial heterostructures, the memory window has been increased from very like in a bigger in scale, which has been increased. So you can see that the sweeping voltage from this one, the memory window has been increased for the instead of like when we are making the axial heterostructure, the memory window can be increased, which has been observed by the after making the nanostructures, which we have observed. And further, we checked with along with my collaborator, we have made the flexible memory stir. Then that we have made a flexible substrate, and then in that one we checked with the different yeah, the flexible angle which we checked, and then we found the we measure the IV characteristics, and then after some particular changes, then it is started deteriorating the devices. So further, still we are exploring further how it can be improved, and the multiple times when we are flexible, like when we make the flexible, how it can be our nanostructures can be withstand. So further, still study is going on that particular one. And another one also, we along with our the collaborator, we made a the solar cell with flexible the structures. Then we like changed as we have done in the photo detector one. Then we check with the this solar cell also. We changed the different flexible the bending angle. Then we measured that the open and short circuit current, like when we measured, and then we found that after particular the bending, then still it is started still our device is able to have a the better performance in that one, the flexible device which we have measured and then we have seen. Further, in another application which we started looking in the different one, like kind of self-cleaning kind of things, like self-cleaning, or we thought of playing with the surface, the modification with help of the nanostructures for with the nano composites, or even the changing the are mimicking the lotus, the effect in our material and structures. So for self-cleaning or different applications, we are thought of doing further studies on that with whatever we made nanostructures. So I will be talking further, and as I have mentioned previously, like our the nature is giving a lot of the providing a lot of ideas, creating curiosity to a researcher. Excuse me. To make further studies on the how it can be applied, and then nature always teaching so many things, and then we have to understand, we have to try to understand what is trying to tell, then it can be helpful, and then we can make use of that the nature. It can be helped in the different applications. So for that one, that before going to that one, that as I was said, in the surface was a different, if you see, like the lotus as well as rose petal, and then rice petty one, and the shark skin, the like beetle insect, the skin, everything. If you see scanning electron microscope, or if you see the surfaces of that one, how it this look like, uh, some kind of very rough surface which you can able to see. So that the these are the some types of that the how the surface is having the difference in terms of like the uh, ilography, or like a hydrophilic or hydrophilic, hydrophobic and hydrophobic the surface. Then when the surface to the to the your water, and then surface angle, how the angle it is making with that one. If you the hydrophilic, if it is less than the contact angle between the surface and to the water droplet, if you are measuring, then we say that hydrophilic. Then hydrophobic, if it is like the surface to the water contact angle is like more than 90, then we say that hydrophobic. And then super hydrophobic is like if it is greater than 150, we say super hydrophobic. Like if the contact angle is less than in between less than 10, then we say that the super hydrophilic the nature of that one. Then there are Young's model and then Benson model. They have created a two different model. If the surface is smoother, then how it can be used, and then if the surface is some kind of making different rough, and also with the help of the nanostructure if we are making, then again the air pockets between the two the structures creating another different one. Then this has been uh, observed and it has been analysis the that Casey Baxter model. Then they have given a two different model, the Young's model and also the Venn model, and then Casey Baxter model. There is the simple two different types of model has been given just for the example which can be used. And we have created as I have mentioned previously, like we have made different structures like the nanowires as well as the axial heterostructures nanowire. And we found that almost the axial heterostructures we measure the water contact angle which is 130 degree, the surface to that the water contact angle when we measured. And then also the stability also we measured till 600 second, then we measured and then we found that it is still stable, then it is not changing anything. And we found that is very the stable when we are making. And also like other only that titanium nanowires when we made, then and again indium oxide nanowire also we made the separately, and then axial nanostructures we made. And then we found that the axial heterostructures showing that very good wettability and very nearly to your the super hydrophobic in nature which we can get. So we have further did for another interesting things which what we have done is that we have illuminated with the UV light. When we are illuminating with the UV light, what we found the interesting thing is that from the super hydro nearly a hydrophobic nature to the hydrophilic nature, it is changed after 60 minutes of the UV illumination. It is changed from the hydrophobic to hydrophilic in nature. It is almost nearly to the super hydrophilic nature which we observed. The only that if you see the indium oxide and then titanium, it is though it was trying to be like a phobic to the philic nature was changing, but when we made axial heterostructures, that it is came to that super hydrophilic in nature after the illumination of the light for 60 minutes. So that was interesting things which we observed. And another interesting thing is that it is not only staying in that particular place like in the a super hydrophobic. If we keep for a while and then it is come back to the original position of that hydrophobic nature, from hydrophilic to the it is kind of smart. The wettability which we observed or the contact angle has been observed after from that hydrophobic to the hydrophilic. Then when we are keeping for a while, then we could observe that again, then it is very quickly the coming back to the original position that was observed when we are having the axial structures when we made it. So that was the interesting thing which we observed in the when we make the nanostructures, axial heterostructures of the nanowire. So further, another things what we have done is that we have the made a nanos axial heterostructures further. Then we studied the post annealing the treatment. When we are having the post annealing treatment, it is started having like from hydrophobic nearly to the super hydrophobic to the hydrophilic in nature. Like super hydrophobic nature came when we have made a 600 degrees Celsius the post annealing in the open air. When we made it, then we have made we could observe that the contact angle has been changed from the hydrophobic to the super hydrophilic nature. But further, when we are increasing the temperature further, then it is started climbing up to the hydrophobic in nature. So from this was the another interesting things when we tune. If you want to tune that particular one, then you have to heat up the like the structure for 600 degree, and then the surface like what exactly happening is that like the surface has been when we are heating further, the surface has been like changed. The roughness of these things has been changed till 600 degree. Then further, when we are increasing to that 800, it has been structural deformation might occur. So that is why, like whenever if you wanted to do, like if you want to go for the super hydrophilic in nature you want, then you can heat up to 600 degree, so that in the open air condition, then it is you can able to change from super hydrophobic nature to the super hydrophilic in nature. So that was an interesting thing which we observed, and then it has been published. So another interesting what we have done is that we have made it was another attempt for us to not only the nano axial heterostructures. We thought of let's make some kind of decorating kind of things, we took a kind of ornament, and then we have a diamond, we have a gold, and then we wanted to decorate it with the diamond. So similar, like after seeing some structures, and we thought, okay, why don't we create some kind of decorating the the nanowire with some kind of nanoparticle to change from the broadband from the UV photodetector to the broadband photodetector. So we with the help of the glancing angle deposition, then we made the nanoparticle decorated on top of the nanowire, in tip of the nanowire, and it is the particle has nanoparticle, the diameter of the nanoparticle has been almost it is distributed almost 7 nanometer. The average diameter of the nanoparticle diameter is, we found that around 7 nanometers in average. And that we have checked with transmission electron HR time as well as we checked. Then we could find that the gold particle has been decorated on the nano wire, and also this observed in the electron microscope. So further we check with the optical analysis with decorated with a nanoparticle called nanoparticle, which made it. So here another interesting thing is that, like if you see from just nano, like when you are decorating the nanoparticle, you were able to see the from UV to visible region also it is increasing, and also band gap also changed because of that the nanoparticle which we have made it. So here if you see the responsibility in the because of the introduction of when we including the gold particle, we could able to see some kind of the responsibility, we could find it in the visible region. So that was another interesting things which we made different structures to make the photo detector in the broader spectrum. And over here we found that that when we made with different the axial heteros, like a nanowire with decorated with a gold particle, you were able to see the rise time and fall time. If you see that, we could able to very quickly within a like a 0.15 seconds, it is able to quickly detect and then come back to the original position. So this has been observed by our the team. Another things which we have made it is some kind of the nano composite we have made with help of the servothermal method, and we made some kind of nano composites like a copper with the cerium, and we have made a copper oxide with the cerium, the doping with the cerium. And then when we are making, then we found that like optimization also we have done, the how much percentage of that particular the cerium need to be doped. It is from the cerium to cerium oxide came, so it started coming. So we have made the particular composition. Then with help of that one, we made a uh, we under the solar irradiation, we have efficiency of that the rhodamine B and the methyl blue has been degraded very quickly. That has been observed. We further like we have made some kind of multi-wall carbon nanotube along with the ferrite material composite which we made it. When we made a composite, then again we very quickly, if you see, like methylene blue was here, and then within 60 minutes that the dye which is mixed in the uh, with the composite, it is reacted and has been like removed from that one. And another advantage of that removing of this particular one with help of that magnetic nanoparticle, like it is like a magnetic the behavior which we have, then means like it can be separated with the help of the magnet. Then the reusability, it can be increased, means like the composite having the magnetic property. So when we are when we are keeping to the magnet, the permanent magnet, even it can be very quickly, like attracted, and then can be removed. The methylene blue or whatever the chemical which is available, it can be uh, uh, removed, as well as like a nano composite further it can be reused further. So that was the another interesting thing which we checked. So another one is that like when we are uh, the optimization, when we are making further people are optimization, what happen is that like we make with help of some kind of material, okay, the composite when we are making, we try with different composition. Let's say like for previously we are saying we have taken the 1.01 gram of multi-wall carbon nanotube, and then 0.04 and then 0.07 and 0.1 gram of the multi-wall carbon nanotube we taken, and then with the composite we made with the manganese ferrite. So like we have to do multiple times. So in order to do the optimization or doping of something materials and different in that one. So what I have learned in during my when I was in Japan, what I learned is that like the quick optimization, that is a combinatorial the synthesis. The combinatorial is nothing but this is the moving mass in the substrate like a holder. This is the source material, then this is the moving mass. Then with help of the moving mass, then right and left, then even able to make the ridge in one side, and then another side is another material ridge. uh, means like the composition, the fusion can be, you can make the fusion. Then with that one, you were able to make some kind of devices, and then the optimization can be done very quickly. So that was the if you see here in the schematic representation, I have taken the titanium dioxide with doping with yttrium. Then what happened is that like we have taken the one move, and then moving mask in the left direction, right direction when we are moving, then we can able to find that the one side is the one particular material. After multiple successful like repeating of that multiple time, then moving the mask from left and right, then you were able to make the layer by layer. And after that one, you can see it can fuse with the heat. Then it is, you can see one side that the one material is rich, and another side is another material is rich. So that in between, if you see that the material fusion can be easily seen, then with that optimization, where you with that one, if you make a devices, so like we have studied uh, the X-ray diffraction analysis when we did, then we found that changing of the like when the one side with the yttrium rich to the titanium, then we could able to see that another phase formation started, like the rutile phase that we made a titanium. Then the when we are increasing the richness of that Y, and we were able to see that rutile phase has been increasing. So with that one, the optimization can be done, like if you are making what composition we require, what kind of things which can be easily useful for the different application, that can be seen. So that is what we have seen. And we have measured the against the electrical with the position as well as the current which we measured. Then one side is rich and another side is another material is rich. Then we could able to see the changes. The optimization can be done very easily and quickly. So that was the another interesting technique. The people can look, those who are looking for optimization of that particular the material, how we need to make any devices. So further these also, like like we can do further tuning of making different materials or reducing the this one. Still there is many things need to be done in this particular the analysis. So with that, I would like to like summarize my talk of this today. Like it is multidisciplinary. It can be used in a different applications and different field, especially from all the like from electronics to like textile, from textile to that flexible things. Everything can be used, and uh, it is exciting for the science as well as to overcome the challenges. With help of the science and engineering, we can overcome the challenges what the people, the human people are going through nowadays. And it can be that again the challenges always giving some opportunity for us to increase our challenges to the opportunity the people can work. Then they can make some kind of product to help the society. And also like when we are making any things, then it should not being the responsible citizen, we have to be like very careful on the environment. And then that once the environment has been affected very uh, like affected very badly, and then it is in directly it is affecting us, directly or indirectly it is affecting our life, human life. So we have to be, whatever we do, whatever the technology we create, whatever the things which we are preparing, then it should not hamper the environment. So uh, to be that one, that is my humble request to that any the people those are working, that we have to be very careful on that particular one to the think on the particular environment aspect. So these are our small group in our institute. This is my email ID, and thank you so much once again, and for the organizer for giving the opportunity and giving our to share my knowledge which I have gone through. Then I'm happy to answer if there is any question. Thank you so much, and then over to you.
Thanks, thanks for your nice talk. So participants, if you have any queries, please type in the chat box, or you can unmute and you can ask me.
I have one doubt, sir.
Yes, sir.
Sir, actually, I want to know about controlling the size of nanomaterial. Suppose we can control the size of the material by some doping agent, by adding the doping agent. But when we are measuring the SEM image, then that size is not exactly in that proportional in which we want. Like suppose if we want to make the 30 nanometer of nanomaterial,
Okay.
or 10 nanometer of nanomaterial, or 20 nanometer of nanomaterial, what we should do?
Yeah,
How we can
actually,
control
like
the size
I'll tell you
exactly?
there's something like we also face the, as I have mentioned, that like we have the thickness monitor meter inside the vacuum chamber. We have
Yeah.
in that one, what happened is that like we grow like a like 100 nanometers of that thickness if we are keeping. Sometimes like still we have to do the optimization on that one, so that it has a different the scenario or the like things. Then we also face the same thing. We grow the 100 nanometers of nanostructures, and then like when we check with your FSM or TAME images, then it is sometimes it is reduced, then that 100 nanometer to that like a 70 or 60 nanometers only grown.
Yeah.
It is happen sometimes because of that either the crystal monitor which you kept, sometimes it might be little bit like a different, or the space like the space between that one, it might be changed, or the it does not have enough the wafer which can able to detect or something. It, but we are also tried the same thing, and then we come to that optimization. Okay, if we are doing this much, then definitely it is having that like this much only. So after that we always try with if it is we want 100, then we go with 120 or 130, so that we can have the this one. So that is the what we done. So sometimes it is very difficult, like the thickness monitor which you are keeping, how we do not know how accurate it can be detected. So still we used to face a problem.
So actually, thickness diameter monitor we can put, but it is not sure that we will get the exact size. It is not sure.
Yeah, that
And
is what, like, see, that is what we have to do optimization. Otherwise, it is further it is difficult. So we
and
have to
one more,
optimize. Then
yeah, one more thing, sir. One more thing. Actually, sir, we are taking the utmost care during synthesis of nanomaterial. But then also in SAM image or FESM image or 10 image, we can see some agglomeration is also coming. Agglomeration of the particles.
yes,
Whatever it
agglomeration
is,
actually, like if you are playing with some kind of oxide materials or gold or metal particles when you are doing, then we are also had some issue when we are making with the gold particle. The
yes,
agglomeration happens. What happen is
yes.
that like the axis, the gold, when we are reacting with the oxygen, it has a tendency that when we are taking outside the with the atmosphere, like the temperature, it is started like the it is started joining with the other particle very quickly. So
But
that is,
but temperature we are keeping generally low only when we are using the gold. Then how
if you
the agglomeration?
if you do the in situ studies, and then you won't find that kind of things, that when you are not doing the in situ studies, then it is always have issues. So we have checked on that particular the aspect as well.
Sir, generally I have worked many places in IITs also. Now I am professor in government organization. But I have seen that whatever steps we are taking, whatever cares we are taking, definitely agglomeration will come.
Yes. So that is what, like, most of the people, they always go with the in situ studies without taking outside of that one. Then they have a different chamber. Then if you go some of IITs, like in IIT Delhi or IIT Bombay, they have a multiple chamber. Once they done, then they transfer that sample to that another chamber to study whether it is like any particular things are happening or not.
Okay, sir. Okay. Thank you very much.
Yeah, thank you so much.
Sir, there is some questions in the chat box, sir.
Okay. Okay.
Srikanth
Super.
PhD, internship available your institute.
Yes, internship we can do. All the things you can always reach us. There is no issue on that one. So internship, my view, I always put it in a such a way that my group always open to the students. Anytime when you are coming, you just ping me that I want to use the facility, and provided if the equipments are, if that the facility is available readily, then you are always welcome to access. Then always you can come and work with us, our group. So there is no restriction in our group. So it is always open, so people can in our institute as well, like my group always open to all the department. They do like all the analysis in our institute and then in our lab. So they also feel that they don't like left, or they don't like feel they are away from anyone. So the facility are created to use, not to keep it idle. So I always feel that one to utilize by somebody. If not me, then somebody can use up that one. So that was the motto. Then you are always welcome to work, or to do your further studies if you require anything. So for supercapacitor, there are something that I'm not with the supercapacitor study. Of course, I was thought of doing something on the supercapacitor. One of my students started, but we couldn't make it. So I may not be able to comment on that one. Of course, you can do the literature review, where you will find it out that what is that the supercapacitor can be material as well as the method as well. For supercapacitor studies, we have used the chemical synthesis method, that's albothermal method we used, and then we made some devices. And we have given to some of my friend. We were thought of making some collaborative with some of other institute, but we couldn't succeed at that one. So, and moreover, that student who was working on the particular field, and then he also completed his PhD, and then he went further out. So reducing the pollution, actually, like still some of the nano composites are using. The efficiency of that one is still, it is questionable, and also the people also, they are not taking care for very, or they are taking very casually. Okay, let it go. I'm just discharging some amount of that one, that does not affect much. But maybe just because of that, they are thinking they are the only one person putting, discharging that contaminated the water to the water body, and they are not thinking there are many people further they are doing. So that was a problem. So that people, we have to be a responsible citizen to make the better life for the upcoming, the better society. Then we have to be a very responsible person, and in terms of the environment, without affecting that one. So we have to do particularly on that one. So that was one. Actually, like I was thinking to work on that particular, the solar, for the solar cell things. Maybe just one student joined, maybe he might be working on the particular one to increase the solar efficiency with the different structures. As of now, we haven't explored in the solar cell, but we could able to do that one. That possibility is there with structures. Then we are maybe we'll be working further for the solar cell in the upcoming years. So is there any other further question? I'm very happy to answer. If not, you can always reach me. My email ID, I'll just put it over in the chat box. Those who wanted to reach me, you can reach me through this mail, or you can ping me through this number. So this is the one. I put it in the chat box. Those who want to make use of that one. My group, our group is always open to have any the discussion or to collaborative or anything. That always welcome.
Thank you, sir. Thanks for your nice talk. So there is no queries in the chat box. YouTube.
So if there is no
thank
question,
you.
I would. Is it okay? And once again, I would like to thank the Professor Sakti Pandi for providing opportunity to share with a very wonderful audience to are creating some kind of curiosity so that it can be helpful. So that was thank you so much again. Thank you so much, sir. Mr.
Thank you, sir. So shortly the feedback link will be posted in the chat box. I request the participants please fill the feedback form. And feedback
I
link.
can leave now, sir?
Yes, sir. Please, sir. Thank you.
Okay, thank you so much.
Thanks. So the feedback for the 28th February is also posted in the chat box. Please fill that also. And today's feedback is also posted in the group. So today evening we don't have any session. So tomorrow we have the two more parallel section. So tomorrow we will meet at 10 a.m. Thank you.
Thank you, sir.
So do we have a session on afternoon? A special session?
We don't have any session today afternoon.
Thank you, sir.
So tomorrow only we have the session.